Word. And then, okay, so can you guys see my screen? I'm screen sharing, I'm recording. Okay.
Yes, Doctor.
Okay, apa-apa soalan boleh tanya. Alright, so today kita nak belajar pasal self-induction. So I know you guys have forgotten about what we have learned because of your exam, but it's okay. So sebelum ni kita cakap pasal induced EMF. Right, where's my pen? So we talked about induced EMF. Okay, so we talked about induced EMF and we discovered together through this chapter that we needed to have a relative motion between the magnet and the conductor, or you needed to have like a change in the magnetic flux. In the magnetic flux. So the relative motion contributed to the change in the magnetic flux. So the induced EMF equation is minus n, what was it? I forgot. Yeah, it's this equation. Okay, the change in magnetic flux over the change in time. And we know that magnetic flux is related to BA cosine theta, or B dot product with A. When you expand it, becomes BA cosine theta. So your magnetic flux is related to your magnetic field, is related to your area, and is also related to your angle. So if you change any of this, which is if you change the B, if you change the A, and if you change the angle of your area, then you are indirectly or directly changing the magnetic flux. And because this happens over time, it is over time lah. Okay, so and when you have when you have more coils, then your induced EMF will become greater. For instance, if I'm comparing between two systems, one system has one coil, the other has 10, but they both have the same magnetic flux. The second system will obviously have more EMF or a higher voltage than the first one, because the first one only has one coil. So the coil plays a part. Okay. What else did we learn? We learned about motional EMF as well. We talked about motional EMF. That concept was a little bit hard, I have to admit. And you guys can go back to my video if you want to revise motional EMF. We talked about when we are in a magnetic field, doesn't matter if it's going in or out, and then you have a conductor that is moving to the right or to the left. From there, you use your right hand rule to find out what is the electron movement. And then from the electron movement, you decide what is the positive, what is the negative. And from there, if you have a wire that is connected to your conductor, then your current will flow from the positive to the negative. Okay, so that is what we talked about. So we have motional EMF, we have induced EMF from the change in magnetic field, induced EMF from the change in area, and also from angle. So that was when we had relative motion. We did something to the system. We had to do something to the system to have magnetic flux. All right, so now we are talking about self-induction. Self-induction ni, we don't do anything to the system. Maksudnya, I have a conductor and I have a coil wrapped around the conductor. This is a solenoid. And the wires is connected to a battery source. Okay, so I am not moving a magnet. This is a magnet. I'm not moving a magnet, or I'm not like flipping the solenoid, or I'm not doing anything to the solenoid. The magnet is not here, but you will still get induced EMF without any external things going on. So the induced EMF comes from the system itself. Okay, so that's the difference between self-induction and the induction that we have learned previously. The induced EMF that we have learned previously, kita kena gerakkan something. We have to do something. We had to change the area and so on. But for the self-induction, the changes in the change in magnetic flux comes from the system itself. Nanti kita akan discover lah how it's possible. So for this chapter, we will talk about what is self-induced EMF, self-inductance, and calculate the inductance of an inductor. Okay, and then we calculate the energy stored in an inductor. So these are your learning outcomes. If you want to study for your exam, you should focus on the learning outcomes because typically these are the questions that will come out. Okay, so let's move on. All right, so self-inductance or self-induced EMF occurs when the changing flux through the circuit arises from the circuit itself. Like I mentioned before, you don't have to do anything to it. You only have to change something in the system itself. So no external factors. So for instance, I have a conductor and the conductor is wrapped with a wire, which is a solenoid, and I have current flowing in the conductor, in the wire. Now, if I try to increase the I, right? I try to increase the I. How am I able to do this? First of all, you need to understand that previously we used a battery which was called a DC battery. DC battery ni, dia does not change in polarity, and does not change in value lah sepatutnya. Does not change polarity, maksudnya positif dengan negatif dia tak berubah. Right? If you say the positive is over here and this is the negative, that is your battery. You cannot flip it. Unless you take it out and then you flip it manually, then you flip lah. But if it's already in the system, let's say this is your circuit, it's only, okay, tak boleh lah, ni short circuit. So ada resistor and a battery. If you say this is your positive and negative, then that is your positive and negative. Dia tak boleh tiba-tiba yang ni jadi negatif, yang ni jadi positif. Tak boleh. So that is a DC battery. It does not change the polarity. That is what polarity is. Polarity is your positive and negative. Does not change polarity. That's the first thing. And then does not value dia constant lah kan. Does not change values. So how am I able? Sekejap saya nak fikir if this is too advanced for you. Kejap. Saya takut saya tercerita lebih sangat nanti susah nak faham. Okay, saya cerita pasal DC dululah. So now kita abaikan dulu apa yang saya nak cakap sebenarnya. I'm just telling you about DC battery does not change polarity and the value is stable lah. Does not change in value. You can't like suka-suka hati change. Okay, moving on. Now I have this solenoid. The I is increasing. The I is increasing. We need to say you increase the current. When you increase the current, of course, everything that changes, this guy does not like it. Sama juga, dia memang tak suka. Anything that is changing, he does not like. Previously, the I was flowing at a constant rate. Now, the flow of I is increasing. Maksudnya, it's changing from 3 ampere and then it goes to 4 ampere and then it goes to 5 ampere. It's not like constantly 5 ampere. It's not like that. So it's 3, 4, 5, 6. It's increasing, right? So this guy does not like it. The conductor does not like it. So it will try to oppose, right? So if this guy is increasing, I want you to decrease. So this guy said, okay, I don't like what is going on. I want you to decrease. So how can I decrease this I that is going on? So the way that I can decrease the I is I create a new current that flows in the opposite direction. So the new current that flows in the opposite direction is this guy in the orange. Okay, so this is the induced current, okay, the orange guy. And because we wanted to oppose the increasing I, we have an induced EMF. So when you have induced current, you will have induced EMF, or if you have induced EMF, you will have induced current. Basically, they come together lah. I can say the induced EMF comes first, or I can say the induced current comes first, but basically they will occur in pairs. If there is induced current, there will be induced EMF. Okay, so now that I want to oppose the increasing I will generate a current, I will induce a current in the opposite direction. And we know that current flows from positive to negative. So I can label this as my positive and my negative. So here there is a battery that is in dashed lines, right? This is dash, right? Dashed lines. So this is the induced battery. It's not from the battery in the circuit. So if I were to write the battery in the circuit, this is my I, it will go this way. This is the battery. Okay, kita akan cakap pasal DC dulu lah. So this is my battery. So current flows from positive to negative. So and then I have an induced EMF over here, which is forming in the conductor. So the conductor is positive here, negative here, or you can label it outside the conductor, doesn't matter. So I will have a positive here and negative here. Nampak macam sama, but the current flow is different. Okay. All right, so now moving on to this one. I is decreasing. Situation number 2, I is decreasing. My battery is still, my battery is still flowing in the same direction. So my battery in the circuit should be this way. Okay, so that is my battery, positive, negative. Current flows from positive to negative. Okay, so now this guy is decreasing. The current is decreasing, of course. The conductor hits this. What does it try to do? It tries to increase it. So macam mana kita nak increase current yang tengah decrease? Macam mana kita nak increase the current flowing in the wire? So obviously we will try to follow the direction, right? We will try to follow the direction so that we are helping. Kita macam give it extra push. We are giving the current an extra push. So we need to be in the same direction. So if I flow this way, this will be my positive. This will be my negative. Remember, current goes into negative and goes out from the positive. So this is my induced EMF. Okay, so something to note here. The battery polarity in the circuit does not change. It did not change even for the first situation, and in the second situation, it's the same. However, the induced EMF polarity is different. This guy is positive and this guy is negative, and the balik for this guy, because it depends on whether the current is increasing or decreasing. Please note that this is the same system. I simply change, let's say this guy is a variable battery. Value dia, macam mana nak buat variable battery tu tanpa cerita benda lain? Okay, anggap je lah kita boleh change the value, change the value of the battery. Saya tak boleh masuk lagi topik tu. So anggap this battery can change the current flowing lah. Okay, so it's the same system, the same battery, but this battery is a little bit special in the sense that it can change the current flowing. So when I change the battery to have I increasing, then induced EMF is this way. When I change the battery to have I decreasing, then this is the induced EMF. So that's why dia tak letak battery sebenarnya, sebab susah nak cerita. Dia tunjuk I increasing or I decreasing je. So you can ignore the battery. I'm just showing the battery inside the system to you so that you can compare it to the induced EMF. Okay, any questions on this part first before we move on to other things? Is everyone okay with the concept? Okay.
Yes.
All right.
Okay.
Okay, so now that we talked about the concept, obviously it comes with the equation. So as the current increases, the magnetic flux through a loop due to this current also increases. So now when you increase a current, let's go back to the picture. When you increase the current, you are actually changing the magnetic flux. You are actually changing the magnetic flux. How? So this is your change in I. Your change in I contributes to the change in B because of this equation. So B is N, number of coils, 1, 2, 3, 4, 5, mu naught I over L because it's a solenoid. So L is your length of solenoid. I is the current flowing. So when you change your I, you have a delta I over here. You have to make both sides have a delta. So this guy has a delta as well. So when I have a change in current, I will have a change in magnetic field, a change in B, and I will have a change in magnetic flux because magnetic flux is composed of BA cosine theta. So when my B has a delta, sorry, ini tak ada lagi. When my B has a delta, my magnetic flux will also have a delta. Okay, when I have a delta in the magnetic flux over time, then I will have induced EMF. Sorry. So that is how it happens. So I increasing, I decreasing, both contributes to induced EMF. You already know about this equation. So you just have to relate it back. So delta I contributes to delta B, contributes to delta magnetic flux, contributes to induced EMF. So it's just like remembering from chapter 19. That's a lot, but it happens. Okay, so chapter 19 cerita pasal B, right? And then chapter 20 kita cakap pasal magnetic flux, if I'm not mistaken. Okay. So the increasing flux induces an EMF that opposes the change in magnetic flux. So we saw this, the opposing change. When the I was increasing, we wanted to decrease it. And the induced EMF terbalik. When it was decreasing, we wanted to increase it. The induced EMF akan oppose this lah. So it depends on the situation. Because of the self-induced EMF, as the magnitude of the current increases, the rate of increase lessens, which then leads to decrease in induced EMF. Okay, so this sentence is a little bit confusing. Let me explain. Because of the self-induced EMF, okay, as the magnitude of current increases, we saw that the I was increasing. So I is, let me pin myself. It's distracting me. Okay. So because I was changing, you had a change in the magnetic flux, which also changes the induced EMF, because if it keeps on changing, induced EMF pun boleh change. And then when the the rate of increase lessens. Okay. Okay, let me say that again. Let me repeat myself. So when I is increasing, right, I will induce an EMF that opposes that, right? So this is my I. Okay, so when I oppose it, I am actually saying to the current, no, I'm not saying, I'm actually pushing back the current so that it stops decreasing or it lessens in the increase, lessens in the rate of it increasing, lessens in the rate, sorry, how do I say this? Lessens the rate of increase, lessens the rate of increase, lessens the rate of increase. Okay, let me repeat that again. So when I have an I increasing, I induce a battery because of because I don't want it to increase, right? I don't like the change. So when I induce the EMF, I am creating an I that flows in the opposite direction. So bila kita ada I in the opposite direction, padahal I yang sebenar kita the other way, so dia akan bertembung, and this makes the rate of increase berkurang. This makes the rate of increase berkurang. So let's say previously the current was increasing 3, 4, 5, 6, 7, 8. It was increasing like that. When the EMF was induced, the rate of increase lessened to 3.1, 3.2, 3.3. Maksudnya dia tak naik dengan banyak lah, dia naik dengan sikit je because ada opposing current. Because of this, which then leads to the decrease in induced EMF. Okay, mula-mula dia naik, okay, tak suka, so dapat induced EMF. Lah, saya kena tulis kat tempat lain. Sekejap need you guys to understand this before kita start mengarut dengan equations. Okay, so first of all, kita have an increase in current, right? Increase in I. So the increase in I is quite a lot. So because of this, we don't like this. The conductor does not like this, so tries to decrease the current. And how do we do that? We do it by having an induced EMF through self-inductance. Induced EMF through self-inductance, or we can just call it self-induced EMF. Bila saya ada self-induced EMF, I am actually opposing the current, which now makes the current to have less increase in I. Okay, less increase in I. So bila the increase rate tu berkurang, induced EMF tu dia tak banyak sangat nak kena oppose. Dia tengok, oh dia naik sikit je. Kita tak payahlah buat induced EMF tinggi-tinggi sangat. So induced EMF ni sekarang, dia tak suka juga. Dia tak suka the increase, tapi because increase ni sikit, induced EMF ni berkurang. Dia berkurang. Tadi dia, let's say dia 5 volt, now dia 2 volt. Sebab dia tak payah oppose banyak sangat. Betul tak? Sebab sekarang dia dah berkurang, air yang dalam wire tu dah berkurang. So dia nak oppose pun tak payah nak susah-susah sangat. Dia cakap tak apalah, kita simpan effort, kita kurangkan kita punya voltage. So now the induced EMF decreases. So that is what this sentence means. So walaupun kita belajar this part and this part, it is important for you to understand up until this part. Ada lagi sebenarnya. And then when the induced EMF decreases, this continues, the I continues to decrease, the increase rate continues to decrease. Maksudnya tadi naik 3.1, 3.2, 3.3, now dia further reduce 3.05, 3.1, 3.15. So the increase rate continues to decrease and then the induced EMF continues to decrease sampai induced EMF tu dah tak ada. Okay, so dia ada sampai dia dah tak ada. So that is the whole story here. Okay, that's the whole story. However, you only have to know increase in I, what happens to the induced EMF, what is the direction of the induced current. Okay. Okay, so with that story, bukan saya saja cerita, with that story kita tahu induced EMF dia induce dengan voltage yang agak tinggi sampai dia jadi voltage yang kosong. And because of that, the increase of current, this opposing EMF results in a gradual increase of current to its maximum value. So current tu mula-mula dia nak naik sampai 5 tau. So 3, sorry tadi saya cerita sampai 7, 8, 9, 10 kan. So current tu nak naik sampai 10 tau. Instead of dia naik 3, 5, 7, 10, dia tak naik macam tu. Dia naik slowly because of the induced EMF. The opposing EMF results in a gradual increase of the current to its maximum value. So dia naik sikit-sikit. So 3.1, 3.2 sampailah dia naik sampai 10. Ni macam jauh sangat perjalanan kan? Tapi tak apalah. So meaning to say, the self-induced EMF menghalang current daripada terjun terus ke 10 ampere. Kita start dengan 3, dia tak terus terjun ke 10, which is very dangerous. So self-induced EMF bagi kita punya current naik slowly. So 3, 4, 5 ataupun 3.1, 3.2, 3.3 dia naik slowly lah. Dia tak terus terjun ke 10. So basically the self-induced EMF ni macam safety factor. Okay. So the opposite is also true. When the switch is open, anggap ni bateri biasa dulu. Kenapa saya minta je ni? Okay, so when kita ada bateri kan, and then we have a switch. Kalau kita tutup, the circuit is closed, wire current boleh flow. When we open the switch, we are opening the circuit, which means that the current will go to 0. However, because of the self-induced EMF, the current yang daripada 10 ampere tu, dia tak terus terjun kepada kosong. Dia turun slow. 10, 9, 8, 7 sampai jadi kosong. Kalau dia terus terjun ke kosong, it's not good lah for the system. It's not good for the circuit. Okay, so self-induced EMF ni is like a safety factor. Any questions about the story? That was like very long. Okay, everyone's okay? All right.
InsyaAllah.
Like I said before, I'm just telling you the whole story so that you guys understand that it does not let the value jump to the maximum value or from the maximum value jump to zero. That was for
Tu saya faham.
of the whole story. However, you guys only need to know when I increasing, what happens to the induced EMF, what is the direction of the induced current, okay, and the equations that come with it, okay. So story tu untuk macam backstory je, okay, don't have to memorize the whole story. Okay, so now let's look at the equation. So self-induced EMF must be proportional to the rate of change of current with time. Self-induced EMF, okay, self-induced EMF dia cakap kena proportional to the rate of change of current with time. Okay, so we start with our induced EMF equation, which is N, change in magnetic flux over time. We expand this, we expand the magnetic flux to be NA delta B over delta T. And we know what B is. B is this guy from our chapter 19 or chapter 20, I don't remember. So N mu naught I over L. So you just substitute that inside. We have the I here, which changes in our system. So only the I is changing. A dengan L dengan N tak berubah. So this guy is a constant. That is why it's outside. So the only thing that changes is delta I. Sorry, it's only I and over time. And because this guy does not change, the N does not change, the number of coils does not change, the length of the solenoid does not change, the area of the coil does not change in this situation. Mu naught, which is the permeability of the permeability of free space ataupun it depends on the type of material that you use for your solenoid, does not change. Then we can say that this guy is a constant and this constant is called L. L is inductance, okay? L is inductance. So L is a proportionality constant. So it basically means a constant called the inductance of the device. So L is this guy over here, which is just a derivation of B and a derivation of magnetic flux. Okay, so the negative sign indicates that a changing current induces an EMF in opposition to the change. We have seen that. Okay, so this is an equation that you need to memorize. And this is an equation that you need to memorize. So yeah, induced EMF or self-induced EMF is equal to minus L change in I over the change in T, where L is this guy, N squared over L mu naught A. Okay. So when we look at this circuit, what is actually the inductor? So we talked about inductance. Inductance, it must come from an inductor. Sama macam capacitance comes from capacitor. And resistance comes from resistor. So we will talk more on what is an inductor later. Kita belajar pasal equation dulu. Okay. So now, let's look at this. The self-induced EMF is proportional to the rate of change of current with time. We talked about this already. This is EMF proportional to delta I over delta T. If current is increasing, right? When current is increasing, the I final minus I initial must be greater than 0. So delta I must be positive. That is when your I is increasing. Maksudnya saya start dengan kosong, I end up with 5, 5 tolak kosong, 5. So positive value. So if current is decreasing, I start with 5, I end up with 3. So 3 minus 5 is minus 2. So the I is negative. So if the guy is positive, then the induced EMF is negative. If it's negative I, then the induced EMF is positive. It is from this equation. Now, one thing to note is, what does it mean by EMF is negative or EMF is positive? Okay. So remember I told you kita kena imagine ada battery kat sini. So battery moves, sorry, the battery it produces a current. So this is my positive and this is my negative. So when I is decreasing, the induced EMF is positive. So dia nak cakap sini positif, sini negatif. Saya tak tahu kenapa dia panggil positif. So to me, this sentence is confusing. The way that you should determine this is to know whether it's opposing or trying to push the I to increase. Okay. So if the current is decreasing, negative I, the induced EMF is positive. It only refers to this equation now. To help you guys in this situation, tak nampak. I don't see how this statement helps to find out the direction of EMF in your diagram. But for the equation, of course, easily you know if it's positive, then you will have negative EMF. If this guy is negative, this guy will be positive. It's only for the equation. Okay. Okay, moving on. So we talk about L, which is the inductance. Kita dah cakap pasal EMF tadi. Now we talk about the L. So L of a coil depends on the geometric factors. Okay, so the number of coils, this is the number of coils. More coils means more inductance. The higher your N, the higher your L. So that's the first one. The core, mu naught. So the material that the coils are wrapped around. So mu naught ni is the permeability of free space or air. So dalam dia kita anggap hollow macam tu. But sometimes you can put conductors such as copper or iron, and it will increase your inductance. So value untuk mu naught ni akan berubah lah. But for our syllabus kita akan stick with mu naught, which is free space or air. So if you change it to a conductor, this will increase as well. Okay, conductors such as copper and iron. And cross-sectional area of the coil, if you increase the area of the coil, okay, this guy becomes bigger, so your L also increases. Length of coil, so this guy becomes lagi panjang, so dia jadi macam ni. Okay, so L is down here. So if I increase my L, let's use a different color for that. If I increase my L, then L will, if I increase my length, right, my inductance will go down. Why did I put it there? My inductance will go down. So just look at this equation. If they ask you, how can you improve the performance of your inductor? Look at your equation. You have N, you have L, you have mu naught, you have A. So you can say, I can increase the area of the coil. I can increase the number of coils. I can decrease the length of the conductor, or I can change the, what do you call this? To change the material that the coils are wrapped around with an iron or a copper or other conductors. Okay, so just look at the equation. This is a legit question. They can ask you that. Sama macam capacitance hari tu kan. Oh, soalan tu tak keluar, sorry. So they can ask you this question. How can you improve your inductor? Okay. So mu naught is the permeability of free space, which is this value, Henry per meter. The SI unit of self-inductance is Henry. Henry. Tak ada nama Henry kat sini. Henry. So 1 Henry is actually 1 volt second over ampere. Just remember Henry, it makes your life easier. Okay, moving on. So kita dah cakap, what have we talked about so far? We talked about EMF, which is minus N delta I over delta T. L. Suka T je N. Okay, and we know that this is specifically for self-induced EMF. Kalau kita cakap pasal induced EMF in general, this equation is the one to go for. But basically, they will work either way because they are the same thing. Okay, but this guy is specific to self-induced EMF because self-induced EMF ada inductor. Okay, and then we talked about L, which is a bunch of numbers, a bunch of parameters, n squared over L mu naught A. Saya tak hafal lagi. N squared mu naught A over L. Okay, so that is your inductor. So these are the two equations that we talked about. And then we talked about what happens when your I increases, it does not like it, tries to oppose. And then kita discuss pasal polarity of the induced EMF. So that is what we have learned so far. Baru sikit je. Now we talked about the power supplied by the battery to the inductor is calculated using P equals to IV or IEMF. We know that EMF is equal to L delta I over delta T. Here you just ignore the negative sign. So you have I, L, di, dt. If I move this to the other side, P dt, Li di. So I can integrate this. Oh, dia tak integrate, sorry. Dia expand terus. So dia expand P, we know that P is the rate of energy or energy over time, right? Or U over T, okay? So here they expand du dt, which is P. So this dt cancels out. You get du equals to Li di. You integrate du equals to integration of Li di. So you integrate Li, you get 1 over 2 Li squared. You integrate with respect to I, okay? I don't know if you know integration yet, but do you guys know integration yet? Tahu tak? Tahu.
Tahu.
Kenapa macam lemah semangat dengan bahasa integration? Okay, you don't have to derive, is what I say every time. You just have to memorize this. You want to derive, you can take calculus in your degree later. Okay, so U equals to 1 over 2 Li squared. This du, when you integrate it, it becomes just U. Okay. So U is the potential energy stored in your inductor. It is equal to 1 over 2 inductance times I squared, your current, I squared. So what do you have to know from this slide? You have to know P equals to I EMF. This refers to the power supplied to the inductor, and U equals to 1 over 2 Li squared. Okay, so that is that. So we have now 4 equations. Basically 3 lah. Yang ni macam dah tahu kan. So 3, 1, 2, 3. U equals to 1 over 2 Li squared. Okay, so this is how an inductor looks like. So it's basically the solenoid itself. But this is, solenoid kan macam panjang kan. Dia rupa dia macam ni in real life lah, in real life scenario. So it is actually like a donut with coils wrapped around the donut. Or it can look like this. But I typically see these guys, not the ones yang panjang ni. This one is more typical lah. Okay. That is your inductor. So when we look at the system, let's look at the system again. So you have a circuit and you have a solenoid. So the solenoid is actually your inductor. Okay, this whole conductor wrapped with coil is your inductor. I know we talked about solenoid, but we talked about solenoid in terms of B. So inductor, we talk about in terms of self-induced EMF. So it's the same thing, but nama lain. Okay, so that is your inductor. So inductors consist of a conductor wound into a coil. When a current flows through it, energy is stored temporarily in the magnetic field of the coil. So U equals to 1 over 2 Li squared. So this is the energy, potential energy. When the current flowing through an inductor changes, so when it's changing, it's saying delta I over delta T exists. The time-varying magnetic field induces a voltage in the conductor according to Lenz's law, which is EMF equals to minus L delta I over delta T. So that's your equation. An inductor is characterized by its inductance, the ratio of voltage to the rate of change of current. So what is this sentence saying? It's basically saying from this equation, L is ratio of voltage over delta I over delta T. That is what it's saying. Where L is n squared mu naught A over L. Did I miss anything? N squared L mu naught A. Okay, I did. So that is the summary for inductor. So now we go to the exercise. Let's take a 5-minute break because I know you guys are like dying inside. Okay, so let's take 5-minute break. You can look at this question or you can take your break for 5 minutes. Let's come back at 11:55 and hopefully refresh to do this question.
It's so cold today, doctor.
Yeah,
It's very cold today. I nearly fell asleep.
tak dengar lagi sekali.
It's so cold.
Why is it cold? Dekat hostel, cold.
I don't know the weather is super cold. I cannot even stay awake.
Pakai baju sejuk. That's so weird that the hostel is
I
cold.
think that will make me comfortable more. Hmm.
Okay, I hope everyone is back. It's 11:55. Kejap, I have a text. Check. Doctor, I wasn't clear about the summary. Could you repeat back? Summary mana? Summary mana? Umar tanya summary pasal apa yang tadi? Sorry, saya baru baca. Doktor, self-induced EMF sama je dengan self-inductance. Yes, self-inductance produces self-induced EMF, produces the induced current. So self-inductance ni macam phenomenon lah. Saya cakap. Self-inductance ni perkara yang berlaku yang menyebabkan self-induced EMF. Dia macam tu. So nak kata self-inductance ni sama dengan self-induced EMF? Not really. Okay. Umar ada kat situ tak? Umar cakap apa ni tadi? I wasn't clear about the summary. Could you repeat back? Summary apa tu? Okay, Umar tak ada lagi.
Doctor.
I
don't know. At the beginning of the class, I hear that you say about something summary like that.
Oh, yang summary chapter 23 and chapter 24 tu
Yes.
Okay, saya rasa saya better suruh ketua bidang keluarkan memo, nanti saya akan share. Okay? I think that would be better kot. Tapi in general, I will divide the class into 2 groups. Satu group akan buat summary on chapter 23, satu lagi group akan buat summary on chapter 24. So orang yang buat chapter 23, dia kena buat a video, 1 minute video explaining about chapter 23, and the other group akan explain 1 minute on chapter 24. However, benda ni individual, so you have to record yourself for 1 minute and then you submit. So that's your assignment to cover for chapter 23 and chapter 24. Faham tak?
Okay, Doctor.
Okay, nanti saya akan suruh ketua bidang keluarkan memo. Hopefully that will be more clear lah. Okay, saya bagi tahu siap-siap je dulu. Okay, nanti kita orang akan share slides, teaching slides yang selalu saya pakai dalam kelas. Saya share chapter 23 and chapter 24. Semua orang akan dapat, like the whole asasi will get it. Okay, so that was agreed upon. Kan sebelum ni saya cakap tak boleh share kan, tapi yang ni diorang kasih, diorang akan modify lah. Okay, so that is about the summary. So now let's continue with the exercise. Tadi Mariam Aisyah tanya saya pasal self-inductance versus self-induced EMF. So the answer is self-inductance is not equal to self-induced EMF. Self-inductance ni adalah sesuatu yang berlaku yang menyebabkan ada yang menyebabkan self-induced EMF. Dia macam phenomenon lah. Macam okay, let's say hujan turun, because hujan turun and ada matahari, you get a rainbow. So this rainbow is your self-induced EMF. Dia product daripada self-inductance. Okay, so self-inductance is not equal to EMF. Self-induced EMF is an outcome from self-inductance. Induced current is an outcome from self-inductance. It's a phenomenon, self-inductance ni. Okay. Okay, so let's look at this example. So 300 turns, so n equals to 300. Length is L, 0.25, and cross-sectional area is 4 centimeters squared. So I have to divide this by 100 squared. Okay, instead of just 100 to make it meters squared. It's connected to a varying current generator. So this guy is saying that the I is changing over time. Yang ni kita tak belajar lagi. Saya hold dulu. Nanti kita akan belajar in more detail about varying current generator. Basically what you need to know is that a generator, dia produce a varying I over time. Okay, itu je. So determine the amount of energy stored when the current is 0.5. So I is 0.5 times 10 to the minus 3 ampere. So U equals to 1/2 Li squared. So ni easy je. You just have to know the equations and then find out what it is. So we don't have L here, we have I. So L is L is n squared, which is just this guy lah. N squared over L mu naught A. Okay, N kita ada. So N is 300, L is 0.25, mu naught is 4 pi times 10 to the minus 7. Constants will be given and your area is 4 over 100 squared. So you will get an L of this guy. Units is Henry. Okay. And then from your L, you substitute into your U. Ni easy je, tak payah. You don't have to think. Okay, next one. A coil of wire with resistance of 0.15 ohms. So you have you have R of 0.15, has a self-inductance of 0.083 Henry. Self-inductance of 0.083 Henry. When you say about Henry, you are actually talking about L. Okay, so L is 0.083 Henry. Selalunya dia tak akan sebut self ni, dia akan cakap inductance. Has an inductance of 0.083 or has a self-inductance of 0.083. So, tapi selalunya dia akan cakap inductance. Self-inductance is rare in my opinion. If a 5-volt battery, so V equals to 5 volt, is connected across the ends of the coil. So we have a coil of wire. So the ends of this coil is connected to a battery of 5 volts. And the current in the circuit reaches an equilibrium value. So this is a hint that the I is changing and it changes up until it reaches an equilibrium value, which is what an inductor does. What an inductor do. Inductors do, yeah. Faham tak? And the current in the circuit reaches an equilibrium value. Previously, I told you if we have self-inductance, it is trying to avoid, when we have self-inductance in the circuit, it is trying to avoid the current from shooting from 1 ampere to 10. So, maksudnya dalam kelip mata, 1 ampere naik ke 10 ampere, which is very dangerous. So when you have self-inductance, it will gradually increase until it reaches the maximum value or the equilibrium value, reaches the max or equilibrium value. Alamak, sorry, tulisan buruk. So we are trying to avoid 1 ampere to shoot up to 10 ampere. So when we have self-inductance in the circuit, it is gradually increasing the I until it reaches the maximum or the equilibrium value. So this is what the sentence means. When you see this, don't panic. This is what it means. So what is the stored energy in the conductor? So first of all, we don't have I here. So V equals to IR, right? V equals to IR. So V is 5. You can solve for R, 0.15. So from here, you get I don't know, 5 divided by 0.15. Can someone calculate it for me? And then it wants to find out what is U. Do we have L? Yes, we do have L. So U equals to 1 over 2 Li squared. 1 over 2, 0.083. Can someone calculate I for me? I don't have my calculator here. What is 5 divided by 0.15?
33.3.
33.3 ampere. Okay, thank you. So 1 over 2 times 0.083 Henry times 33.3. So you will get U, which is a potential energy in joules, 46.11. I hope that's correct. I hope we got it correct. Okay, so again, this is easy. You have to know V equals to IR. Find out what is I. You have to know the equation of U. So I think the equation for self-inductance is going to be easy unless you don't know what is the polarity of the induced EMF. Part 2 je saya rasa akan susah sikit. Okay, moving on. If an inductor carrying 1.7A current, so So you have I, 1.7A, stores an energy of 0.3 millijoule. So U equals to 0.3 times 10 to the minus 3. What is its inductance? So it's asking you what is L. So U equals to 1 over 2 Li squared. We have U, which is 0.3 times 10 to the minus 3, 1 over 2. We don't know what L is, but we know what is our I. So this is, then you can solve for L. How much energy does the same inductor store? Does the same inductor store if it carries 3 ampere current? So this was the first situation. For the second situation, it's using the same L, but it is now carrying a different current. So 1 over 2, the L that they got is 2.08. So you use that value again, 2.08 times 10 to the minus 4. And now your your I is 3. Dalam situasi kedua ni, dia pakai inductor yang sama, dia tukar current to be 3. So that's the difference. So now this is your answer, 1 over 2. This is your L, this is your new current. Any questions so far? Sebab kita dah habis exercise on on self-inductance. Everyone okay? No questions?
Okay.
Okay, let me see the chat. Okay, no chat as well. All right, let's move on to the next subtopic. The last one, just called mutual inductance. So tadi kita cakap pasal self-inductance. Dia berlaku seorang-seorang, macam Syok sendiri. Now we have a friend. So for this chapter, explain mutual inductance and its application in transformers. Calculate the voltage and current of transformers. So mutual inductance ni, I would say the tahap kesenangan dia tu sama macam self-inductance. Again, self-inductance punya part yang susah is just knowing the polarity of the induced EMF. So please tackle that if you have a problem with that. Okay, so mutual inductance, the changing current in the primary coil. Again, we have friends here. One is called the primary, your friend is called the secondary. This is me, and maybe this is Shasha, right? So I have a change in magnetic flux. When I have a change in magnetic flux, I am changing the magnetic flux that Shasha experiences because we are like close together, right? So if I, how do I say this? If I am, okay, let's say ada orang simbah air kat saya. Shasha is next to me. So Shasha akan kena tempias air tu. So this is how it happens. So if I change my magnetic flux, Shasha will experience some of it, some of the change in magnetic flux. So when Shasha experiences a change in magnetic flux, Shasha can also have an induced EMF. Okay, so this is the situation for mutual inductance. We start with two friends. One friend ada increasing or decreasing current. The first friend, which is me, self-induced EMF. Okay, I am doing a self-induced EMF. Saya shock sendiri, cakap saya nak berubah-ubah until I get an induced EMF. And because of the self-induced EMF, we have a change in magnetic flux. The increasing current also changes the magnetic flux, and because of the change in magnetic flux, Shasha also experiences the same change in magnetic flux. So if I have a value of, macam mana nak buat? I lupa dah. Oh, okay. If I have a change in magnetic flux, like this is the value, this is the parameter. My value is 10. Shasha will experience the same change in magnetic flux, which is 10. We will experience the same change in magnetic flux. So what is different between me and Shasha? So let's say here we have like 10 coils. Let's use a different number. I have 12 coils. 12, n equals to 12. Shasha, sebabkan dia muda lagi, n equals to 5. Remember, EMF is equal to minus n change in flux over the change in time. So if I change the n, even though we have the same magnetic flux, Shasha will have a different EMF than I do. I will have a greater EMF than Shasha because my n is 12. Shasha is 5. 12 times 10 is 120. And then 5 times 10, which is Shasha, and Shasha is 5, times 10, which is the magnetic flux, is 50. We will have different EMF, even though Shasha punya EMF datang daripada saya. Okay, so that is mutual inductance. Okay, again, I'm going to repeat myself. We have two coils. The primary coil has a certain number of coils. Okay, so this coil number, the N is called NP. Susah nak sebut. Primary turns, primary number of turns, N subscript P. And the second coil is called the secondary, NS. Okay, primary coil has an external battery or external AC generator. The battery can increase or decrease the current. And because of the increase and decreasing current, there will be self-inductance. From the self-inductance, I will have self-induced EMF or self-induced current. And because of the whole situation going over here, I will also have a changing magnetic flux. And the changing magnetic flux they can extend kan, magnetic flux kan, it just goes everywhere. So the magnetic flux goes to Shasha, the secondary coil. That's what S. So the secondary coil experiences the same magnetic flux. The only difference between primary coil and secondary coil is the number of coils. So NP is not equal to NS. NP is not equal to NS. Dia memang akan berbeza. Kalau dia sama coil, kalau dia sama number of coil, dia tak akan jadi an application. Dia akan jadi macam, tak tahulah jadi apa. Jadi pelik lah. Buat apa nak buat benda yang sama kan. Okay, so basically memang kena berbeza. Okay, so with that said, that's your theory. This is the equation. EMF equals to minus M delta IP over delta T. So the induced EMF comes from the current in the primary coil. Nanti kita akan cakap pasal what is M later. Okay. So again, EMF comes from the primary current, primary coil punya current. Sebab Shasha tak ada, the secondary coil does not have an AC generator. Dia tak ada bateri pun. So dia dapat magnetic flux tu, the change in magnetic flux from me. Okay. Okay, so the application of this. Mesti ada application kan, kalau tak apa susah nak buat, menyusahkan hidup je nak kena belajar. So the application of a mutual inductance is a transformer. You use transformer in your house, kat power generator, power generator is called electricity generator. Power generator lah, kat tempat yang plant tu lah, plant yang generate electricity. So you use transformers there. So a transformer is generally a 4-terminal device that is capable of transforming an AC current. Please hold on to this first. Let's just assume that we have an increasing and decreasing current. Kita akan belajar pasal AC ni. Input voltage into a relatively higher or lower AC output voltage. So I can start, the primary coil can have 10 ampere, while the secondary coil can have 5 ampere. Boleh. Asalkan the change in magnetic flux, voltage, not current. Voltage. Asalkan the magnetic flux is the same. Okay, so over. So P, this is the primary, is equal to the change in magnetic flux, secondary, sama. Okay, walaupun voltage mereka berbeza because of the number of turns or the number of coils. Okay, so a typical transformer has two closely coupled coils that we have seen just now. Contoh, or more coils, boleh juga lebih dari 2, that share a common laminated iron core. So basically kita akan share one conductor, tapi number of turns kita berbeza. The conductor akan connect the first one, primary, with the secondary and transfer the magnetic flux. Okay, dia macam jadi linkage lah. So the magnetic flux travels through the conductor to the secondary coil. Okay, so transformers. An AC transformer consists of two coils of wire. AC means alternating current. It means the current changes of wire wound around a core of soft iron. So this is a typical diagram of a transformer. So you have a primary coil, secondary coil. Primary coil will have NP turns. Secondary coil will have NS turns. Let me make this bigger. Kecil tulisan dia. Okay, so you will have a primary voltage, VP, primary current, and the magnetic flux from this guy is transferred to the secondary via the transformer core or the soft iron core or a conductor. And you will have a secondary current, secondary voltage. Secondary voltage and primary voltage ni yang kita selalunya nak kita nak tentukan. Kita nak specific value lah. Okay. So let's talk about the description of the transformer now. So the side connected to an external input. Kita tahu yang ni kena ada input sebab dia nak generate self-induced EMF. The other side called the secondary is connected to a resistor and has NS turns. Dia ada resistor supaya dia tak short circuit. You don't have to memorize this. In the secondary coil, voltage is induced by a varying magnetic field produced by the primary coil. So I told you the magnetic flux from the primary goes to the secondary. The core is used to increase the magnetic flux. Kiranya, if you have a conductor, the performance of the transformer is increased. Provide a medium for the flux to pass from one coil to the other. The rate of change of the flux is the same for both coils. Like I mentioned before, this guy is equal to this guy. P. This is S. Dia akan sama. Tak boleh berbeza. Transformer mesti sama. So this is the main point here. Okay. So a transformer, what does it do? It is a device for increasing or decreasing an AC voltage. When your secondary has more coils than primary, then it is called a step up. Sebab dia increase the voltage. When your primary is less than your secondary coil, it is a step down because you decrease the voltage. What does a step up mean? It goes, let's say we start with 1 voltage, it goes to 10 volt. Step down goes from 10 volt, goes down to 1 volt. Okay, so 1 volt ni datang daripada primary to secondary, primary to secondary. So how is it possible to achieve 10 volt even though the magnetic flux comes from the primary? Remember, we talked about the N. So if NS is greater than NP, then you will get a higher voltage. If NS is less than NP, then you will have a lower voltage. Okay. What is this? Okay, so this is the induced EMF for primary. This is the EMF for the secondary. Okay, dia nak cerita pasal ratio. Okay. So when we have these two equations, so EMF for secondary is number of turns of secondary over magnetic flux, times magnetic flux. EMF for primary equals to minus NP times magnetic flux. If we divide these two equations together, let's say, memang saya nak divide. So if I divide equation 1 with equation 2, I will get EMF secondary over EMF primary equals to minus NS over minus NP delta benda lah ni, magnetic flux over magnetic flux, which cancels out because they are the same thing. So this guy cancels out as well, becomes positive. So I am left with this ratio. So EMF secondary over EMF primary equals to NS over NP. So dia boleh tanya macam ni. So if the secondary coil has 10 turns and the primary coil has 100 turns, the voltage of the primary coil is 5 volt. What is the secondary coil? So use this ratio. You have the number of turns and you have the primary voltage. So solve for the EMF of the secondary coil. So that is how they can ask you. Okay. Senang je saya rasa. And then we have another equation, which is related to power. So the power in secondary coil and the power in primary coil. So power is IV or VI. This is V, this is I. So secondary EMF, secondary current, you get the power for secondary. It is equal to the power in primary. So EMF primary times current primary. So you divide these two equations. So ini dia tak divide. Dia rearrange dia. So I bring the primary EMF over here and the secondary current over here. So I will get EMF S secondary over primary EMF equals to primary current over secondary current. Now, apa yang kita kena note kat sini is that dia terbalik. The S is down here, the P terbalik lah. But previously we talked about N and EMF, they are the same. So P with P, S with S. But when it comes to I, dia terbalik. So this is something that you need to be aware of. Okay? So how do you remember this equation? I don't have any tips except for you to derive it if you want, or you just have to try to remember this. Okay? Either derive it or you just have to memorize it like this. So N is always proportional to EMF, inversely proportional to current. N proportional to EMF, inversely proportional to current. Okay, so if this is NS, ES, 1 over IS. So NS over NP, EMF secondary, EMF primary. Yang I kena terbalik, so IS is down here, so which means that the primary must be on top. Okay, that's one way of doing it. All right, so transformer applications. No, this is not it. Just my mind. This is where you use transformer. Yes, you have a transformer in here as well. Okay, banyak lah sebenarnya. You can just Google it. Okay, so any questions about mutual inductance? It's the end of this chapter. Kita akan masuk pasal AC current. Oh, sorry, AC lah. No questions? Wow. Okay, that's good. This subtopic tak ada exercise. Can we take like 5-minute break and then we continue at, let's continue at 12:30. Okay, 12:30 p.m. Okay, so let's continue 12:30 p.m. Next chapter. Tak boleh, I cannot postpone that. We are late. Okay, so come back at 12:30. Okay. Hello. I hope everyone is back. It's 12:30. Let's continue with chapter 21. So chapter 21 is about the alternating current, or AC. AC. AC means alternating current, but basically selalunya orang cakap AC current. AC voltage. I think ada. AC current. Dia akan cakap AC current walaupun AC tu dah alternating current. Okay, so it means the same thing. So in this chapter, we will learn about AC generators and AC circuit. Dekat Instagram unit fizik dah ada both chapters, chapter 20 and chapter 21. If you find the videos are more helpful than my lecture, boleh juga study pakai those videos. Alright, so for your exam nantilah. Okay, so AC current. In previous studies, we exposed more on DC, which is right, which is the electricity flowing in a constant direction or possessing a voltage with constant polarity. Constant polarity means dia punya positive and negative does not change. It cannot be flipped, right? So DC is a kind of electricity made by a battery. Okay, name, general knowledge. Certain sources of electricity, most notably generators, naturally produce voltages alternating in polarity. Okay, so what does that mean? So basically it means that within this circuit, an alternating current punya generator, dia akan rupa dia macam ni. This is the voltage source, walaupun dia cakap alternating current. This is the voltage source, this is the symbol, and my current can flow from here if I set it to be positive here and negative here, or I can just flip a switch and I can change my polarity to be positive here, negative here, and my current will flow from here. So an AC current, dia punya direction of current boleh berubah, and we can control it lah. Okay, so that's the difference between a DC battery. So DC battery looks like this. AC battery is a circle with sign punya sign, not SIGN, it's sign function. Sign function inside of a circle. Okay, so that is the symbol untuk diagram. You have to know this diagram punya symbol because they will use it. And if you don't know what this circle with a sign means, then you will just assume it's a regular battery, which is wrong, okay? So either as a voltage switching polarity or as a current switching direction back and forth, this kind of electricity is known as alternating current, okay? So that is that. So this is how an AC generator looks like. I believe we have seen this around in, I don't know. I don't think I've seen it before. Or maybe I have. I don't know. Okay, so this is how it looks like lah. If you see it kat tepi jalan, which you won't find it tepi jalan, so you know that, oh, this is a AC generator. So don't know if it's helpful. Okay, so this is a diagram of an AC voltage. We've seen this diagram before. I believe we've seen this when we talked about magnetic force. With our magnetic force, we could produce this coil, it flipped, right? Because of the magnetic force. When it flipped, it produces a movement, and the movement produces electricity. Okay, so we have seen this diagram before. I don't know if you guys still remember. And another generator is used. This is electricity generator. It gets mechanical energy from the turbines, from steam, and also from the steam tu tolak, steam kan push upwards, so it rotates the turbines. When we have motion, it converts into electricity. Semua juga macam kat sini, we have motion from the magnetic force. So the motion is converted into electricity. So it's always like mechanical work to electricity. Mechanical work to electricity. So that's a generator in general. Okay, you don't have to know this one. Okay, so the learning outcome for this chapter is to explain the working of an AC generator. kita akan belajar. Explain the sinusoidal nature, which is why I mentioned about sines. So AC current is a circle with a sine function inside. So because it has a sinusoidal nature of the induced EMF and current. Right, write the equation for AC current and voltage. This one is easy. Okay, let's move on. Okay, so it is a device that converts mechanical energy to electrical energy. It consists of a wire loop rotated by some external means. Tadi kita dah tengok the turbines were rotated by steam. In other cases, we have falling water, heat by burning coal, or a dynamo, right? A dynamo converts mechanical to electricity as well for your bicycle. And this is how it looks like for magnetic force. Yang ni magnetic force juga. So generator selalunya akan pakai this concept. Okay. Okay, so the basic operation of a generator. Banyaknya words. Sekejap, let me try to minimize it. Okay. As the loop rotates, let's go through this together. As the loop rotates, the magnetic flux through it changes with time. Okay, so magnetic flux, let's talk about magnetic flux. Magnetic flux equation is composed of BA cosine theta. When the loop rotates, you are actually, kita ada magnetic field, right? This is our B. When the loop rotates, you are changing the A. You are changing the A that is interacting with B. Changing A that is interacting with B. When you have a change in A, you have a change in your magnetic flux. When you have a change in magnetic flux, you will get induced EMF. Okay, kita dah belajar pasal ni. I'm just repeating myself. And a current in the external circuit. From the induced EMF, we will get a current, an induced current. Let's see apa yang penting nak cakap kat sini. The ends of the loop connected to, okay, tak penting. Connections to the external circuit are made by stationary brushes in contact with the slip rings. Magnetic force is perpendicular to the length of the wire. The EMF is generated in the wires BC and AG. Kita dah belajar pasal ni, so I don't think I'm going to repeat. Kat sini, this is not the important part of this chapter. So if you want to know how this rotation works, go back to chapter 19, I think. I explained about this guy. I talked about the rotation axis. We talked about torque, and I talked about how it moved. Okay, so it's the same thing, except that now we are calling it a generator. From the loop that was rotating in the magnetic field, now we are calling it a generator because it changes mechanical energy to electricity. Tu je perbezaan kat situ. The mechanism, how it works is totally the same. Okay, so now let's talk about this diagram. It is talking about the loop and versus the B. I told you when the coil rotates, you are actually changing the area that interacts with the B. An area that interacts with the B, area is direction dia macam ni kan. Remember, it's magnetic flux is, this is like, I think this is at this point it's 100 times already I've mentioned this. Magnetic flux is BA cosine theta, where A is, what do you call it? The normal to the surface. Okay. We are talking about area in terms of the normal to the surface, which is, normal is always the perpendicular, 90 degrees to the surface. So this is the surface of the coil. This is your direction of A. So direction of A needs to be parallel to the direction of B for your magnetic flux to be maximum. Okay, I think you still remember that part. Direction of A needs to be parallel to B for your magnetic flux to be at the maximum. So when B and A is completely aligned, cosine theta is basically cosine 0, and this is equal to 1. So it's the maximum. So when your coil, the punya normal is parallel, the normal of your area the normal of your area is parallel to your B, walaupun the opposite, you will get a lot of B interaction with A. So dia nak cakap, okay, kotak ni besar kan, maksudnya banyak lah your magnetic flux. So when you rotate the coil to sideways, sekarang ada angle, tadi mula-mula macam ni. Now it's rotated. So the amount, your normal of A, this is your normal. So now the angle between the normal and B is changed. The angle between your normal and B berubah. So let's say it's 25 degrees. So BA cosine 25 will not be equal to the maximum value. It will be something that is smaller. So, or in other words, benda B yang interact with A is only this much. Macam mana kau? Dia macam kecil. Macam mana nak tunjuk ni? Yeah, so the A that interacts with B is only this much. So you get a smaller box. The box represents the magnetic flux. And then when you further rotate it, the angle of your normal to B is further increased. So the area that interacts with B is only this much. So lagi kecil magnetic flux. And then when your normal is totally perpendicular, patutnya kosong lah. Tapi dia assume kat atas ni ada surface. So this is the amount of surface that interacts with B. Magnetic flux is that much. Tapi selalunya kita akan cakap kosong je. Kita akan anggap surface tu very nipis. So tak ada area kat atas. Tapi yang ni ada area sikit. So boleh lah. And then again, the coil rotates and rotates and you get your changing magnetic flux. So the magnetic flux keeps on changing when your coil rotates. So this is the point of this diagram. Or if you don't understand this diagram, basically you just look at this diagram, look at this equation. You know when your coil rotates, your area changes, the area or your angle between A and B changes. So your magnetic flux changes, okay? So as the loop rotates, the magnetic flux through it changes with time. The magnetic flux through it changes with time. What is magnetic flux? Magnetic flux is the magnetic field lines that go through the area. So banyak ni je yang masuk, banyak ni je yang masuk area, banyak ni je yang masuk, banyak ni je yang masuk. So it changes. Okay. So an EMF produced by the coil is given by Faraday's law. So N change in magnetic flux over time. So when I expand this equation, I get NB dA cosine theta. Remember our coil is rotating. So either I can say this, my area is changing, or I can say that the angle is changing. Okay, in this case, they say it's easier to say that the angle is changing. So they say that, okay, let's define omega. Omega is angular frequency. You've seen this one before. Omega is also equal to 2 pi f or 2 pi over t or theta over t. Theta is 2 pi. Kalau full circle, theta is in radians. Okay, bear with me. Saya nak cerita pasal equation dulu. So if I have induced EMF as NB dA cosine theta dt, and I want to substitute theta with omega, sebab omega ni speed. So if I know what is the speed of my coil, I can just put it into my equation. But how do I put it into my equation? I substitute theta with omega. So how do I substitute theta with omega? Theta is equal to omega t. You just rearrange the equation. So now you can put in theta as omega t. Now your equation becomes NB dA cosine omega t over dt. And because we said that the change is given by the angle, we can say that the area is constant. You just put it outside. So NBA d cosine omega t over dt. So ddt is derivative. Derivative of cosine omega t is omega sine omega t. So this guy is the derivative. So you just plug it in. So NBA omega sine omega t is your equation for induced EMF of a rotating coil. Okay. This is the equation. I know it's like macam panjang gila cerita tapi last dapat equation je. It's okay. Sometimes the explanation yang paling panjang tu will help you some for anything else, benda lain lah. Okay, so basically for this slide, you have to memorize this equation. MBA omega sine omega t. What is omega? Omega is your angular speed or angular frequency. What is omega? Omega can be 2 pi f or 2 pi over t, capital T, period. Or it can be omega equals to theta over t. When you substitute the theta into your equation, it is theta equals to omega t. Okay, so that is your equation. Do we have to know this one? Kejap, A equals to 2LA over 2 cosine. This is specifically for the coil in your magnetic field to this one. Is this one? No, where is it? Yeah, this one. So this is L, A over 2. Okay, this is L and this is A over 2. So dia cakap kalau nak kira area, it's 2L A over 2 cosine theta. So I don't think you have to memorize this. You just have to know how to calculate an area of a coil, which is easy. So you don't have to memorize that. Okay. Okay, so why does an AC current behave like a sinusoidal function? Oh, we have time. Why does it behave as a sinusoidal function? Because it changes in time. The value changes in time, and also the direction can change in time. So here, this is a graph of induced EMF over time, okay, over time. And if I go through this diagram, I can say that the voltage, kita buat macam ni lah, 1, 2, 3, no, I want to make this easier for you to understand. 1, 2, no. Let's say this is 2, this is 4, this is 5, this is 5, 3, 5, 6, 7, 8, 9. Oh, dia tak start dengan kosong pula. Extend. No, I need to start from 0. Korang. In the meantime, please take some breaths. Don't have a panic attack. 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. Okay, boleh lah. Okay, so yang ni saya dah label time dia siap-siap saja je so that I can, it's easier for me to explain. And then let's label this as 5 volts down here. And this is minus EMF not or equal to minus 5 volt. Jangan buat ni lah, dibahagi. Ni or This is or. Okay, so my induced EMF goes from the maximum, can go up to the maximum, can go up to 5 volts, and can go as low as minus 5 volts. Or if I say this in parameter punya words, my induced EMF can go up to EMF naught and can go as low as minus EMF naught. Tak kisahlah EMF naught tu value dia apa over time. Okay, so at time 0, my induced EMF is 0. At time 1, my induced EMF is 5 volts. At time 2, my induced EMF is 0 again. At time 3, my EMF is minus 5. At time 4, my EMF is 0. Time 5, my EMF is 5. 0, minus 5, 0. So here it changes according to a sine function. A sine function always starts from a 0. A sine function always starts from a 0 unless there is a phase change. Tapi kita tak belajar phase change kat sini. Kita belajar last semester. So kat sini kita start from 0, it follows a sine. Kalau cosine, dia start macam ni kan. Cosine dia start macam ni. So tak boleh. Kita kena start dengan a sine function. A sine function starts from here. Do not start your graph here. Do not start your graph here. That's a cosine. So that is different. So your induced EMF follows a sine function. Okay, EMF is 0 when the plane, okay. How does it relate to our coil just now? Let's go back. Okay, so here, I know this starts from the maximum, tapi kita boleh anggap dia start pada sini lah. So this is 0, let's say 0, and then I move to the maximum, which is 5. So from here to here, the induced EMF looks like this. So 0, and then this is my 5 volt, and this is the time that it completes this whole part. So this is, I only reach this part. So this is my graph. I start from 0 and I increase slowly to the maximum 5 volt. This is the maximum 5 volt. This is 0, this is 5 volt. I increase slowly. And then after I reach the maximum, kita akan tengok di sini pula, dia akan slowly turun. When I reach the maximum, it slowly goes down until it becomes a 0. So it slowly goes down until it becomes a 0. And then after it becomes a 0, it slowly goes up. But now the current flips. Dia akan flip. Kat sini dia tak tunjuk flip, tapi dia akan flip. But walaupun dia flip, dia akan reach a maximum value. The maximum value is a negative. So it's a minus 5. So it's a maximum value, but since the direction of current terbalik, dia jadi minus 5 volts. So this is how it relates to the sinusoidal graph. Okay, let's go back to the graph. Naik, lepas tu reach maximum, turun, reach 0, dia naik balik, tapi sekarang ni dia naik, tapi current terbalik. So dia jadi negative 5. Lepas tu turun balik, turun ke 0, naik balik, turun balik, naik balik, tapi negative. So this is what happens. The current punya direction flips. When it flips, it becomes the negative part of the induced EMF. Okay, so this is specific to AC. Specific to AC circuit, specific to AC current, AC DC. Sorry, AC battery, AC voltage. AC DC pula. DC is direct, right? AC voltage. Specific, specific. So you won't see this happening for a DC battery. DC battery positif setiap masa. AC battery boleh ada positif, boleh ada negatif. Okay. So the induced EMF, kita boleh cakap since, okay, let's look back at this one. Since this guy reaches a maximum value of EMF naught, and it follows a sine equation, so I can say my EMF changes according to this equation, EMF naught sine omega t. Okay, so at time 0, my sine is a 0, so my EMF naught times a 0, so EMF at this point of time is a 0. So is it 0 here? Yes, it's a 0. So you will use this equation to find out what is the exact value of EMF at a certain time. So it follows this equation. So you can also substitute omega with 2 pi f because it's the same thing, or 2 pi over period. And your induced current is I naught sine omega t. So the current also follows the same sinusoidal graph like your EMF. And your EMF is V equals to IR. Okay. R je yang tak ikut. R tak ikut the sign. I follows the sign. EMF follows the sign. R is a constant value. It does not change. It's not an AC resistor. Okay. Alright. So DC generator tak payah belajar. Tak cover patutnya. Okay. So let's look at this. We have 5 minutes. Do we have time? Yes, we do. Okay, so last question and then we will be over for class, with class. So an AC generator consisting of 500 turns, so 500, 50 times 150 centimeters squared rectangular coil. So here they gave you the area. So you don't have to memorize the equation for area. Either you have to know how to find the area of a square or they will give it to you. So 50 times 150 centimeters squared, change it to meters squared. It rotates at a rate of 100 RPM. So omega, angular speed, is 100 revolutions per minute. This is not the SI unit. You need to change it to radians per second. So how do you do that? In a magnetic field of 1.5 Tesla. So B equals to 1.5 Tesla. I think we should continue later lah. Nak kena cerita balik pasal ni. Takut korang dah lupa. Okay, let's continue with class on Thursday, which is tomorrow. Oh, tomorrow korang ada lab tak? So class dah habis Tomorrow korang ada lab tak? I mean like bukan lab saya, lab kimia. No one is here. No one's. Everyone's sleeping already.
We don't have chemistry lab tomorrow, doctor.
Is it after Raya? Oh, tapi lab semua dah tunda kan? I mean everything is online.
I don't think there will be any like practical.
Okay, alright. So tomorrow saya tak payah habiskan at a certain time lah. So let's start our class tomorrow at 11. I aim to have class for 1 hour and 30 minutes. Is that okay for everyone? Separuh je. Okay, so tomorrow 11 to 1:30. 1:30. 11 to 12:30. Okay, tu je. Any questions before I turn off the Zoom? No questions? Okay, kesian belajar lama-lama. Okay, so hopefully that was okay. If you find it to be confusing, please try to discuss with your friends or look at my YouTube videos. Okay, so I'll see you tomorrow. Have a great rest of the day. Untuk orang tak puasa, selamat have lunch. And untuk yang berpuasa, have a good berbuka later. Okay, bye-bye. Take care, everyone.
Thank you, doctor.
Welcome.
Thank you, doctor.
Thank you,
Thank you, doctor.
Bye.
Thank you, doctor.
Doctor.
Bye-bye. Welcome.
Thank you,
Thank you,
doctor.
doctor.
Excuse me. Teams 2. Bye.